mass is 25 kilograms, and radius of gyration with respect to the mass center is 175 millimeters. So actually we can compute mass moment of inertia about the mass center and about any axis we like. And there's a groove here which has a radius of 75 millimeters, and there's a cable or a rope, I don't know, is wrapped to it. And in this problem, what is given is we pull it with a tension of 30 newtons, and this angle theta is 0. So we just pull it horizontally. The coefficient of friction between ground and this disk is quite low. The static coefficient is 0.1 and the kinetic is 0.08. And we are asked to determine the acceleration of this mass center and the angular acceleration of the disk. Also, the friction force between the ground and the disk are asked, okay? But we have no clue that whether it's going to slip or not. So we have to make an assumption and then check if it is true or not. So what I'm going to do is, that's my figure. I draw the free body diagram for what is given. So what I have is my T, which is 30 newtons. I have the weight mg acting at the mass center. This is my friction force. Now, how do I determine its direction? And this is actually N is the reaction force. It's simple. That's my friction force. But how do I determine its direction? That's important. For the friction force, the direction should be determined correctly, okay? We can't say if we find it negative, oh, it's the other way around. No, that would be too many assumptions, okay? So I should guess its direction correctly. Number one, suppose there were no friction and say I'm just pulling it through the mass center. So what's going to happen if there were no friction? This point would slide to the right. Am I right? And the friction force would try to prevent this. So friction force being left towards left would be okay if T were at the mass center. Now, if T moves downwards, what would be the moment of T about the mass center? It would be a counterclockwise moment. Am I right? Again, suppose there would be no friction between the ground. If the moment is counterclockwise, the wheel would start rotating counterclockwise, and the friction force should try to prevent it. Again, it should be to the left. Am I right? So taking it to the left is okay because some of the forces will try to move the disk to the right. Friction force is trying to prevent this. Also, moment of this force is trying to rotate it counterclockwise. Moment of this friction force is trying to prevent this motion, okay? So it should be to the left. Is this clear? Any questions on direction of friction force? That's critical. And yeah. Clockwise moment. Yeah, that would be tricky. Suppose T were here So it's trying to move the mass center to the right. Friction force to the left is going to prevent it, but the moment of T about the mass center is clockwise, so it will try to rotate it clockwise. So a friction force trying to prevent that would be to the right. Actually, in such a case, what you would do is you may just put friction force in one direction and try to compute its value. Then also you have to compare it with the maximum friction force. Okay, so there will be actually two components of the friction force. One would be to prevent the acceleration of, or to slow down the acceleration of the mass center, which would be to the left. The other one would be to the right, that would try to resist the angular acceleration. And total friction force would be the sum of these two components. That would be a little more trickier, okay? And depending on what the distance is, how it's going to move, etc., one of those might be larger than the other, so the total friction force would be the sum. But here we are lucky, both create the same direction. Okay? So I don't know whether it's slipping or not, but I can write this. I can sum up the horizontal forces and equate it to the mass times the acceleration of the mass center. What do I have? I have the 30 newtons of T minus an unknown friction force is equal to 25 times the unknown acceleration of the mass center. So I have one equation, but two unknowns. I can't solve them. Well, actually, for the vertical direction, I just omitted this. Since there is no motion, no acceleration, I can find N, which is equal to the weight. N is the reaction force. And I will need it to check friction. That's why I need it. So the contact force is actually 245 newtons, which I will use. But here I have two unknowns, but only one equation. I can take moment about the mass center and equate it to mass moment of inertia about the mass center times the angular acceleration of the disk. So what I have is moment of T, which is counterclockwise. Okay, the distance is 75 millimeters times 30. And moment of the friction force, the distance is 200 millimeters times the unknown friction force is equal to 25 times, this is the radius of gyration about mass moment of inertia. So I take its square. So the product is IG times alpha. The trouble, one more unknown. Okay. The friction force is the first unknown. Acceleration of the mass center of the disk is the second unknown. Angular acceleration is the third unknown. Here, I have two choices. One is when I pull it, the disk is going to slip. In that case, what would be the friction force if it's slipping? Mu k times n, am I right? It has the maximum value. So I can substitute it and I can solve for these two. The other option is it is not slipping. Then friction force is an unknown value, but it should be less than or at most equal to mu s times n. Okay? So I have two choices. Which one would you choose? Also, remember the coefficient of friction were quite low. The static coefficient of friction was 0.1, kinetic one was 0.08 or 8%. Would you expect slipping or not? Well, I will assume I won't expect slipping. So the friction force is another unknown, and I will check if it's less than mu s times n or at most equal. But if it's slipping, if it's rolling without slipping, I have a kinematic constraint. Am I right? Acceleration of the mass center should be r alpha, but actually this is the x component, which is this. And since alpha is counterclockwise, actually I should have a minus sign in the front, okay? Alpha is like this, but positive AG direction is like that. That's why I have this minus, and that's a kinematic constraint that relates the two. So I have three unknowns, three equations right now. If it's rolling without slipping, it's a constraint motion, okay? Is this clear up to here? Then I have three equations, three unknowns. I can do the solution. Acceleration of the mass center turns out to be 0.425 meters per second square. Angular acceleration is negative 2.12 radians per second square, which is clockwise. Actually, if AG is like this, alpha would be clockwise. That's something we would expect. And the required friction force for rolling without slipping is 19.38 newtons. Okay, now I have to check if I have this condition, okay? Because rolling without slipping occurs if I have sufficient friction force, and this is the required value. What is the maximum available value? Actually, I have checked the two friction forces. One is static, and the maximum static friction force is 24.5 newtons. If you have initial slipping, this would be the kinetic coefficient of friction, but the required value is smaller than both. So actually we have that much friction force. So required friction force is less than static. Also, it's less than kinetic. So we would expect rolling without slipping. If this number were in between, then if it starts from rest, it will roll without slipping. But if somehow it starts slipping because maybe you increase this T, then it will continue slipping. But for our case, whatever happens, it won't slip because it's smaller than even this value. So actually we got the acceleration of the mass center, the angular acceleration of the disk, and also the friction force. Okay. Any questions? Now I will try the same problem with coefficient of friction values half given in the book. Okay. So mu s rather than 0.5, I will assume 0.05, and mu k rather than 0.08, it's 0.04. So the maximum friction force, static friction force, becomes 12.25, and maximum kinetic friction force is 9.18 newtons, whereas the required value was something like 19.38. So it will roll with slipping. Okay. In that case, what shall I do? The solution would be simpler. There wouldn't be a kinematic relation between the acceleration of the mass center and the angular acceleration of the disk. But we know the friction force, okay? It's mu k times n. So you can substitute it into here, get the acceleration of the mass center. You can use moment of the forces is equal to mass moment of inertia about the mass center times the angular acceleration. Again, substitute the friction force here, which you got, get the angular acceleration. And you won't have this, you may check it because it's slipping, and the solution yields the acceleration of the mass center is much larger. Why? Because you have T minus a smaller friction force, and the angular acceleration, again, the moment of the friction force is less, so it would be larger than the previous value if that were the case. Okay? So any questions on this problem? Is everything clear? Okay, then we may try another problem. We have a slender rod like this, whose length is L, and it's on an incline like this with a very small frictionless wheel here, okay? What it says is the slender rod of mass M and length L is released from rest in the vertical position with the small roller at end A resting on the incline. Determine the initial acceleration of this point, okay, which is A. So what we may do is this. We have to draw the free body diagram. I will assume x direction along the incline, y direction perpendicular to it, okay? This will help me to sum up the forces. You might as well use an xy coordinates where x is horizontal, y is vertical, but that would simplify the equations, okay? What I'm going to have is a reaction force Fa, which is in the negative y direction due to contact here. I have a weight mg acting at the mass center. And what I will start doing is I will take moment about this point A. You could also take moment about G and equate it to Ig alpha, but what I'll do is I'll take moment about A. The reason I can eliminate this unknown reaction force Fa in that equation, okay? So this is the first equation I'm going to write. Its moment of the forces about A is equal to Ig alpha, where Ig is mass moment of inertia about the mass center, plus mass times acceleration of the mass center, and its moment about G, which is actually the distance that I will compute. So what I'm going to do is, actually, what is moment of forces about this point? Moment of weight is 0. Moment of Fa is 0. So this Ma is 0. Okay? Then I will write Ig alpha And for a slender rod, the mass moment of inertia about the mass center is 1 over 12 ml squared, which is tabulated in the book, okay? So we can get this from the book times alpha. Then I have to calculate MAG and then take its moment about the mass center. Now, in doing that, what I'll do is a little trick. I will write an expression like this. Let me just show you. The slide is a little shorthand. Let me explain what I'm doing here in this line. I say acceleration of point A is equal to acceleration of the mass center plus the acceleration of point A with respect to the mass center. Okay? So actually what I need is this so that I can substitute it into here and I'm going to take its moment, okay? But we know that AA is, with our coordinate system, AA magnitude I. Am I right? It's like this. Along the incline. Am I right? Then this relative acceleration, AA with respect to G, has two components. AA with respect to G, tangential, and AA with respect to G, normal. Am I right? And this has a magnitude alpha r. This has a magnitude omega square r. And they are perpendicular to each other, okay? But if the rod is released from rest, at that instant, what is omega? It's 0. Am I right? Because it's released from rest. So this normal component drops. What I'm left with is just the tangential component, okay? This one, which I'm writing, okay? So what I have is, in this expression, I can write it like a scalar expression, okay? The normal acceleration, the tangential acceleration is like this. A G with respect to A tangential, okay? And A with respect to G tangential is opposite of that. And it's perpendicular to the slot. So when you take its x component like this, the angle between the two is theta, and this is how I get this expression. Okay? So I can substitute everything into my moment equation, and without having the reaction force, moment of the forces were 0. This is Ig alpha. This is Ag, okay, this one. And then I have M rather than, yeah, M, A, G, but in terms of AA, and that's the moment, okay? So what I have is alpha and acceleration of point A rather than G. The trouble is, again, I have two unknowns. What's asked is this, but I should also determine the angular acceleration of this rod when it is released. So I have to solve the other two equations. Well, if you choose x and y like this, as you see, there is no motion in y direction. You can find FA, it's mg cosine theta, and then you can write sigma fx is equal to magx, and we have the component of mg along x direction, which is mg sine theta, which is equal to m ag. But I won't substitute ag here. I will, from this expression, solve for ag, which is aa minus this, okay? So these two equations are two equations in acceleration of point A and the angular acceleration of the rod. From one of the equations, say this, you can solve alpha in terms of others, substitute it into the other equation, and you can find acceleration of point A, which turns out to be g sine theta over 1 minus 3 over 4 cosine squared theta. Okay? Any questions on this problem? You could as well solve the same problem, not taking moment about point A, but you could also take moment about point G, okay? Because you can find FA very easily and take its moment about G if you like, and still you would get the same answer. So here, actually taking moment about point A does not provide, I would say, much useful answer, because finding the reaction force is not something difficult, okay? So you could also use mg is equal to ig alpha. You can directly get an expression for alpha from mg equals ig alpha, and then you can substitute it into this expression and still get it, okay? So here, as the good old Turkish saying says, the taking moment about point A, attığınız taş ürküttüğünüz kuşa değmedi. But it's up to you, okay? You could use mg is equal to ig alpha as well. Any questions? Okay. Well, that's a problem I like very much, but I think the authors do not like it as I like, because it just exists in the 2 editions of the book, but not in the other 3. And right now they have the 9th edition. I don't know whether it exists or not, but that's a very interesting problem. It looks very simple. What it says, determine this maximum force P such that this wheel will not slide on the cart, okay? So let's read the full problem statement. Determine the maximum horizontal force P, which may be applied to the cart of mass capital M for which the wheel will not slip. But as you might guess, when you push this, the mass center of the wheel will resist this acceleration. So relative to the cart, it will start rolling backwards. We can't avoid this, okay? But it shouldn't slip. The wheel has a mass lowercase m, rolling radius r, that is the radius of the wheel is lowercase r, and radius of gyration about its mass center k. The coefficient of static and kinetic friction between the wheel and the cart are mu s and mu k respectively. And actually, if we do not want it to roll, to slide, then, and also we would like to apply the maximum P, actually the friction force between the cart and the wheel should be mu s times the contact force, which is the maximum one, okay? As soon as you exceed that P, the friction will not be sufficient to prevent slipping, and it will start slipping. So we will have the maximum friction. Also, if it's rolling without slipping, then it's going to have a constraint motion. That is, we will have a kinematic constraint. So we may start with that. We can think that there's a contact point between the cart and the wheel, which I call P. So the acceleration of the cart, which I show with C, should be equal to the tangential acceleration of that point on the wheel. So what I have, what I should have is the tangential acceleration of contact point is acceleration of the cart, and it's actually equal to acceleration of the mass center of the wheel plus R alpha at the instant it starts to roll, omega is 0, okay? And also, for this P to be maximum, we will have the friction force as its maximum value, mu s times m. So keeping these in mind, I can draw the free body diagram of the wheel. I have the weight mg, I have the contact force n, and since there's no vertical motion, n is going to become mg, am I right? That's trivial. And then I will say sum of the forces in x direction is equal to magx. And the friction force is the only force in x direction. And just at a moment, think that friction force is 0. So that's 0. When you push the cart underneath this wheel, what's going to happen? That's my wheel, that's the cart. Wheel, because of its mass, will remain stationary. The cart would move forward. Am I right? So the friction force on the cart is trying to prevent this. The reaction would be in this direction, okay? Or actually, what is trying to move the wheel is the friction force between the cart and the wheel. And we know its value, it should be the maximum value, mu s times n, which is mg, and it should be equal to m times acceleration of the mass center. So actually, since mass is the same and non-zero, I can get the relation acceleration of mass center of the wheel is the coefficient of static friction times g. This is one equation. Then I can take moment about the mass center of the wheel, and it's equal to ig times the angular acceleration of the wheel. So The friction force is mu s mg. Its moment is r, and it's counterclockwise. That's why this is positive. Is equal to Ig is mass times the mass moment of inertia square times the angular acceleration. So I get an angular acceleration, which is mu s g r over the radius of gyration square. So actually, I can determine the angular acceleration. I can also determine the linear acceleration of the mass center from the given things. And also, if it's rolling without slipping, we should have this condition, okay? Acceleration of the cart should be equal to acceleration of the mass center of the wheel plus r times alpha. But currently we don't need that. We have these two accelerations. Then I will move to the cart. And when I draw the free body diagram of the cart, I will have the reaction force of this friction. Now, we should be careful in action-reaction pairs, okay? These two are opposite. I have the reaction of this N here. I have the weight of the cart, which I don't need. This is the ground reaction, which again, I won't need. This is my P. So what I'll do is acceleration of the cart times mass is equal to sum of the horizontal forces, okay? So what I'm doing is, yeah, I'm using that relation. And actually, I have an expression for AG, which was here. And I substitute alpha as well. So I have these. Then I have an acceleration for, I have an expression for the acceleration of the cart, which is actually this. I know its mass. And I substitute the forces in x direction. So it's P minus FF is equal to mass times acceleration of the cart, which is actually this from the wheel relation. So if I take this to the other side, I can get the maximum force I can apply. So that's the maximum force I can apply, which is mu sg, mass of the wheel, mass of the cart, 1 plus radius of the wheel square over the radius of gyration of the wheel square, okay? Any questions on this? Okay, actually this example concludes force mass acceleration method. On Wednesday, we may start work energy relations. I have just 10 minutes. I don't want to rush. And you may just go over direct application of force mass acceleration method in the meantime. If you have any questions, feel free to email me so that we can discuss, and see you on Wednesday if there's no questions.